He'll speak about upper and lower bounds on the VC dimension of tensor network models. Our first touching with AI.
That was the learning to decompose tensors. So here it's not less applied, but thank you very much. So I'm Guillaume, and I will talk about upper and lower bounds on the VC dimension of tensor network models. And I think I had to miss a couple of questions. I think, did you speak about tensor networks already? Not yet, right? Tomorrow there will be lots of talk. Yeah, exactly. So I have the burden of introducing that to you, which is I'm actually, it's not a burden, the chance to introduce you to the magical worlds of tensor networks for the one of you that don't know what they are. And then once I've introduced those models, I will talk about their VC dimension. So how we can apply these kind of models in the context of machine learning, and especially here the question that we are looking at with my master student Venush Kavari about the VC dimension of these classifiers, of this model that you can build with tensor networks. So yeah, we will start with a brief introduction to tensor networks and tensor decomposition. So who here is familiar with tensor networks? Okay, good. So there is a proportion of you that are. So tensor network, what are they? Mainly, not mainly, but one way to see them is a graphical notation, diagrammatic notation to represent operation between tensors. It has been introduced mainly in the quantum physics community, like in the 70s, 80s, like Feynman diagrams are related to that. It's sometimes called Penrose notation. And it's really like a way to represent complex operation on tensors, basically contractions between tensors in a graphical way. So here the idea, I will not reintroduce what is a tensor, right? We will think mainly of a tensor as a multidimensional array of numbers here. So a vector is simply a one-dimensional array of D numbers here. M is a matrix of size M by N. So two-dimensional array of numbers, and a higher order tensor T here, D1, D2, D3. And so in tensor networks, we represent tensors as nodes in a graph. And the arity of a node, the number of legs, I will call them leg, of a node represent the order of the tensor, right? So a vector has just one leg because it has one index. A matrix has two legs because we have two indices, and the third order tensor has three legs. Okay. And so in these graphs, so now we know what the vertices represent. The edges represent contractions. So contraction is just a summation over a common index. So for example, if I have two matrices, A and B, so here A is a vertex of degree 2, so it's a second order tensor, it's a matrix. B as well, I will put on the legs the dimension of the legs. Right? So here A is an M by N matrix, and B is an N by P matrix. And I'm allowed to connect together legs that have the same dimension. Okay, and this corresponds to a contraction. So here, the resulting thing, when I get those when I take those two matrices, I connect the two legs together. The remaining graph that I have has two free legs, right? So two legs that are not connected to any other leg. So this represents a second order tensor. We have 2 degrees of liberty. So this is a matrix. And this L represents this contraction, so this summation over K going from 1 to N. So the resulting object, right, has 2 degrees of freedom, I1 and I2, and it corresponds to having this contraction over K. So of course, it's just the matrix product, right? So which represent the classical matrix product. So what can we do if I take two vectors, right, U and V, I connect of the same dimension, then connect their leg together, I will obtain a scalar, right, the zeroth order tensor, and this is just the inner product between U and V. I can do that with tensors. If I have two tensors of the same shape, S and T of size D1, D2, D3, I can just connect each of their legs that has the same dimension to obtain a scalar, and this thing actually defines a natural inner product on the space of three-dimensional tensor or other three tensors of size D1, D2, and D3. From this, of course, we can define a norm. If I take the inner product of a tensor with itself, I get the squared norm of the Frobenius, the squared Frobenius norm of this tensor, right? Which corresponds to, it's really like, if I take this tensor, let's just see it as a big vector of size D1, D2, D3, it's like it's 2 norm. One thing that we can do, I actually don't have a slide, I will write it here on the board very briefly, is also one thing that happens if you take, for example, two vectors, and you put them one next to another, so U and V, let's say this is of size M and of size N. This actually corresponds to the resulting graph that I have as two free legs, right? So it's a matrix. It represents a matrix of size M by N. And this is the upper product of those two things, right? So this is actually equal to U V transpose. This rank-one matrix. Okay. And if I put higher order tensor together next to one another, for example, two matrices, I put them one next to another, it will be the tensor product, so fourth order tensor, which is just the order product of those two matrices. A nice one. So if I have a matrix, square matrix, I am allowed to connect its leg with its older leg, and this corresponds to this contraction. This is simply the trace of a matrix, right? So for those of you that are familiar with partial traces, this is a very nice way to think about partial traces. Partial traces, I have a tensor with a bunch of legs, and I'm just connecting some of its legs with themselves, and this gives me the partial trace operator. And so we can represent the idea of this graphical notation is that we can represent some operation between tensors without having to write all of those summations, right? So the idea is that for an expression like this, I want to take a third order tensor T, multiply it on its first mode by A, second mode by B, third mode by C, which we can think, right? If T represent a bilinear map, for example, we can think of it as changing basis of the input and the output, but it just boils down to this. And this diagram represents these three summations here. So when we get very complex operations, it allows us to reason with them, to manipulate these objects without having to carry those summations around. All right, so it's a bit the same spirit as Einstein notation. We want to make those expression more easy to manipulate. It goes a step further. We just have those diagrams now to look at. Another interesting thing that we can do, that we can allow ourselves to do, is we can present this in several ways. We can present them as hypergraphs. We could say, okay, now I'm allowed to connect more than two legs together. And this corresponds to a contraction over this time not only two indices, but three indices. So I can, for example, define this kind of three-way inner product, where it corresponds to summing UI, VI, WI. And this black dot represents some kind of an hyperedge. Another way to think about it is that actually this hyperedge is nothing else than this tensor here, the identity tensor, right? So we talked, there was a talk last year, we were talking about the subranks, where this object is very important, especially if the D here is not the same as the dimension, but this is also sometimes called the copy tensor or the spider tensor in the quantum physics community. It's basically this diagonal, hyperdiagonal tensor with only ones on the diagonal. Good, so those are tensor networks, a very brief introduction. Any question on that? Everything clear? So I can just clarify that the order in which we do the contraction doesn't affect the actual output, right? It's actually, you can make it very formal. So the complexity will not be the same, of course, like determining the optimal order of contraction. If I give you an arbitrary tensor network, is an NPR problem. But the order in which I do my contraction doesn't impact the result, right? So it's really a well-defined object like that. Good, so now we can present common classical tensor decomposition using this formalism, these tensor networks. For example, the Tucker decomposition, right? So the idea of tensor decomposition is I have a tensor, potentially higher the tensor, and I want to decompose it into the product of small building blocks. And so one such decomposition, the Tucker decomposition, corresponds to taking this tensor T, of size D1, D2, D3, and expressing it as a core tensor G that ideally is smaller, right? G is of size R1, R2, R3, and we expect that those kind of rank, so this is actually the multilinear rank of the tensor, the size of this core tensor, the minimal size of this core tensor, multiplied by 3 factor matrices. Okay. So this is one decomposition. The idea of decomposition is, of course, to, at least pragmatically, in machine learning and in data science, is just to, one main application is to reduce the number of parameters. Right? So here, potentially, I have an object of size D1, D2, D3. If, let's say, R1 is equal to R2 is equal to R3 is equal to 2, I'm reducing the number of greatly, right? If the rank is constant, I get an exponential reduction in terms of the parameters. I have the sum of the dimension. So this is one decomposition. I will just list 3 of those. Another one that is very popular in quantum physics and in numerical analysis is the Tensor Train decomposition, which gets its name from the fact that we decompose a tensor as a train of tensors. Right? So we have this chain graph where most of the tensors, when I have a higher order tensor, will be third order tensor, and I just have the first one, the last one that are second order tensors. Right? So I decompose it in this way. And here, the number of parameters. One thing that is interesting in this case, so let's say we have the same dimension everywhere and the same rank everywhere, R1 equal to R2 equal to R3. Basically, we get something which will be of size, the order of the tensor times dr squared. Right? So we have as many of these, roughly as many of these set-order tensors. So we get to something now that if p is the order of the tensor, we get to p d r squared parameter instead of d to the n. Right? So this is interesting because we get a really, for very high order tensor, this is very nice decomposition because we get something that is linear in the order of the tensor in terms of the number of parameters. So in the physics community, this is known as matrix product state, this decomposition. Another decomposition is the CP decomposition, the canonical decomposition, or the parallel factor decomposition. It was one of the first introduced by Hitchcock. And this one can be represented in this way. So maybe you know the CP decomposition in the sense of I want to write my third order tensor T, for example, here as a sum of rank 1 tensors, right? AR, outer product, BR, outer product, CR. So this is the same thing, right? Just the graphical notation of writing that. If those A1, right, if my matrix A that I represented here correspond to just taking those vectors A1, A2 up until AR and putting them as columns of a matrix of size D by R, and doing the same thing for B and C, then this expression is exactly the same thing as this summation of outer product of rank 1 tensors. All right, so this is the classical notion of, the most common notion of rank that we know for tensors is this CP rank, right? So the rank of the tensor often is the smallest R such that I can find this decomposition, this expression, and graphically it represents like that. And actually we can think of this for every graph structure, we can define a notion of rank. So for example, here I can say, okay, I fix this structure, and I ask what is the smallest R that I can find such that I can find this decomposition. And this gives us the notion of rank. But I can do that for TT as well, for the tensor train. I can say, okay, I fix this idea that I want to decompose my tensor as a chain of third order tensor, except the first and last. And what is the minimum value of those things, or 1 or 2 and or 3, that in physics people call bond dimensions, right? Correspond to kind of the bounding between different particles, yeah, I'm really not a quantum physicist, but I learned along the way by manipulating those objects. But so this is, you can ask what is the smallest R 1 or 2 or 3 that I can find so that I get an exact decomposition or an approximate one. Good, so this is our CP decomposition. And there's lots of ways to decompose the tensor. So I show you CP, Tucker, Tensor Train. You can have Tensor Ring, which in quantum physics is like matrix product state, but with periodic boundary conditions. We have hierarchical Tucker, which is kind of a tree tensor network thing. We have this PEPS, which is projected entangled pair states, which is basically this two-dimensional lattice, kind of the extension of the tensor train to the two-dimensional lattice. You can do that to 3 dimensions. And in physics, they do a lot of things with tensor train. It's very efficient to simulate many-body systems, quantum many-body systems with matrix product state, but moving to to two-dimensional system is very difficult. Like a lot of the things that we can do very efficiently with tensor train becomes very tricky as long as we go to these PEPs or even higher dimensions. But so here, I will not be talking about how to apply that to do efficient computation or computing ground state of quantum systems, but more how we can use that. These models, one way to use these models in machine learning, and talking about RBC dimension. We will consider 3 tasks, classical machine learning tasks. The point of binary classification. So we want to learn a function f, right, that just assigns to each possible input in an input space X some label, -1 or +1, from a sample. Right? So we have a data set that is drawn from some unknown distribution. And we want to, and we suppose that each yi here is some kind of realization of f of xi, the corresponding outputs, maybe noisy, maybe not. But we want to learn this function from this data set. Right? So binary classification. We'll talk a little bit like the result that I will present. We will focus mainly on classification, but most of the results that I will present apply also to regression, where now what we want to learn is a function whose output are real numbers instead of just binary labels. Right? And also it will apply to completion. So completion, which is a classical problem in machine learning involving tensors, is the idea that I have a tensor X, here P, order P tensor, and I want to recover this tensor only from a subset of its entries. Right? So I observe randomly some of the entries of the tensor. This is my set of observed entries omega here, and the name of the game is to recover X. So this has application, for example, in recommendation system. Right? If you have a matrix, in this matrix, you can put the ratings of your users on items. So for each user and items, you have a rating. But for most items and most users, you didn't observe the ratings. But by assuming some low rank structure in this matrix, which has which is founded in the sense of the relation between user and items, we can assume that it can be explained by the few number of latent variables. Then we get that this matrix is low rank, and this problem, of course, become less imposed, right? Because if I just say I can fill them however I want, I can do whatever I want. But if I say, okay, now I know that X is a low rank tensor, then I get a lot of structure that I can exploit to infer those missing entries. So this is the kind of three problems that our result apply to, and we will focus on binary classification. And actually, completion, we can see completion as some form of regression as well, right? We can think of it as being regressing from the set of indices, so that not each input is actually an index of this tensor, and we want to learn a function that goes from this notation with the integers from 1 to d1 and so on. So mapping p-dimensional indices to the corresponding entry in the tensor. We can also, that completion, we can cast it as a regression problem. So now is there any question on this? That's clear. Yeah.
I mean, if you class completion as a regression problem, then you need to run the regression problem many times somehow. So don't you want the completion to be somehow not entry-wise, I would guess?
So here, you have this unknown tensor, and your function is really like this function that goes from the set of indices to the real numbers. And what you observe, and you can think of it as my unknown distribution is on x times y, right? Is I sample an index randomly, and then I observe x of the corresponding entry. So this tensor is basically my ground truth function that I'm trying to learn from random observations. You can also generalize like this notion of completion is, you can think of it also as learning a tensor from linear measurement. In the sense that you take your tensor and you get here this measurement or particular, because it's like you take this tensor and you multiply it by canonical basis vector in each direction. But a more general way, you can think of it also as recovering a tensor from linear measurement, where basically what you observe is each time you draw randomly a bunch of vectors, as many of the order of the tensor, and then you contract the tensor by all these vectors, and this is your observations, and you want to recover it. It's a more general. Yeah. So now to go to learning, I will just introduce rapidly the statistical learning framework. So in supervised learning, as I was saying, we have a sample S that is drawn from this unknown distribution on the product of the input space and the output space. And this is where, either if we are in binary classification or in regression, we have an hypothesis class. So we consider a space of function that goes from X to Y, in which we will look for the best function. And we have a loss function. So the loss function is something that will allow us to, oh, and there's a typo here, sorry. The loss should be from Y times Y to R. The loss function will allow us to evaluate the quality of predictions, right, made by our model. And so the goal of supervised learning is to find the hypothesis in a hypothesis space that minimizes the risk, the true risk. So the risk is what is the expectation for xy drawn from this unknown distribution of my loss function, right? So the loss of my hypothesis evaluated at x and the real output y that has been drawn from the distribution. So this is what I want to minimize. Of course, we don't have access to D. This is an unknown distribution. So what we do empirical risk minimization instead. So we assume we have this sample S, and instead of minimizing the true risk, which we cannot, we minimize the empirical risk, which is just the average of the loss of a given hypothesis on my training data. So this thing is an unbiased estimator of this one, right? I'm just averaging over realization of this random variables here, of this random variable, which is the loss of hxy. Okay? And so we want this empirical risk to be a good proxy to the true risk, right, of our hypothesis. And so basically, we want the empirical risk to be close to the true risk. This is what we call the generalization gap, right? Because we are minimizing the empirical risk. If we are guaranteed that this is close to the true risk, then we will have a hypothesis that generalize well to new examples that are drawn from this distribution. And this generalization gap depends on two things. The sample size, of course, the more, this is the law of large numbers, the more samples I have, the more the mean converges to the expectation, but also the complexity of my class of function. And this is where the basic dimension will kick in, right? So will be a way it's one way to measure the complexity of H and to relate it to how my generalization gap shrinks to zero as both my data goes to infinity or the size of my, or the complexity of my hypothesis space is less and less.
So what do you do when this data is inconsistent? So when like there are several y's for the same x?
That's correct. It can be part of your you know, we have a distribution on x times y. So my distribution could be, okay, my ring data is a binary classification problem in 2D.
Okay.
I have really my data is like this. I have a true hyperplane and I draw a point randomly. If it's at the left, I will label it by plus. If it's at the right, by minus. But then I had some noise. I will correct some points. So sometimes with probability 1 pair, for example, I get not the right label. And it's okay, right? It's in the distribution. So this I could observe, well, in this case, it will not really happen if we are really on the whole plane, but it could happen that you have the same point with different labels. It's just part of the noise.
I mean, even if you have like a perfect, complete set of functions, if H is a complete set, in this case, your risk would still be, you could not max it out, right? It would still be not zero kind of.
Yeah, and the risk will often not be zero. The minimum of the risk may not be zero.
Right, because in the perfect case.
Even in the perfect case, because you may have noisy data.
Yeah, okay.
For example, I think that you can think of a classical model is your data is generated by this process. You have a linear model, but you have some noise that corrupts. You have a true function, which is a linear function,
yes.
But then your output is corrupted by this noise. So in this case, the minimum risk will be something of the magnitude of epsilon.
Because then you still try to get a function that does it, rather than like a function with noise.
And you try to get the
try to then say like, okay, I'm actually enlarge the class to also map the noisiness in them. But
you don't want to learn the noise. Like the thing in learning is you don't want to learn the noise.
I mean, in quantum, right? The noise is God given. I mean, you know, it's not that you have a deterministic model underlying.
But you cannot be, but the model that you get may not be deterministic. You may have a model that actually learns the noise here, that actually learns that there is an epsilon and that can predict.
Yeah, it's just your hypothesis class was.
So in this setting, we are in the most simple setting where we fix our hypothesis class, like that's really right.
You can't use it.
No worries. Any other question? So yeah, so this idea of complexity of H, for example, in the most simple case where H is finite, then you can get this kind of result, right? So with probability 1 minus delta, the true risk will be bounded by the empirical risk plus this term that decays to 0 as n goes to infinity, and this is the size of my sample. And but the size of my hypothesis play a role here, right? I get this term. So the more complex my hypothesis is, the larger it is, the more sample I need to reach the same kind of accuracy. So this works only if we have a finite H, and if F is infinite, then we cannot do the same analysis, but there is several measures that we can use to get this kind of generalization bond, right? Like bounding the gap between the true risk and the empirical risk as a function of always the number of samples and some measure of complexity. And so one of those is the VC dimension. So here, this is one bond that we can get, where VVC is the VC dimension of H. So one measure of complexity. So what is the VC dimension? Intuitively is the maximum number of points that hypothesis class in the hypothesis class we are considering, H, can separate in all 2 to the n ways. So more formally, if I have a set of hypotheses, right, function from x to -1 plus 1, the VC dimension will be the largest number of points, so the largest n, such that there exists n points that are shattered by H, meaning I can, like if I look at every possible classification that I can do using my hypothesis in my hypothesis class on this fixed set of points, I can achieve all possible 2 to the n labelings of my data. So for example, for linear models of classification, like this thing, we can show that in D dimension, the VC dimension is D plus 1. For example, in 2 dimension, I have 2 points. I take those 2 points. Well, I can any labeling that I can do, minus, plus, plus, minus, I will be able to label them. Right? With 3 points, I can take those 3 points. If I put plus, minus, minus, I can separate them. If I take minus, plus, minus, I can separate them, and you can see that this will work on, right? Now, for any set of 4 points, you will not be able to find all the to realize all the labellings with a linear separator. Right? So for any set of 4 points, you can always take the two that are the further apart and give them the same label, and the other label to the two other one. And you will not be able, I cannot separate linearly those two classes, right? You cannot find a hyperplane that separates the two. Then what we show here, with the ends, is that the VC dimension in 2 dimensions of linear classifiers is 3. So the maximum number of points that was able to shatter. And you can show more generally that this will be for the, if I consider the VC dimension of all these affine classifiers, so I'm missing some parentheses here, but it will be D plus 1. And there is often, but not always, a relation between the number of degrees of freedom in your hypothesis class, when you have a parameterized hypothesis class, like it is here. Right here, every function is of the form, the sign of W transpose X plus B, where W and B are my parameters. I have D plus 1 of those, and turns out to be the VC dimension of that. So it's not always as an equality, but often you have this relation between the number of parameters of your class of model and the richness of the expressiveness of this class of function. Yeah.
You said, I mean, linear classifier. So where does the fact that you're looking for linear things or quadratics in the definition gets into?
Also, it's in the example, right? The definition is for arbitrary class of hypothesis. Like for any class of hypothesis, any set of functions, I can talk about the VC dimension, which would be.
So in your example, linear is the hypothesis.
Is the set of hypotheses, yeah. So if I consider this set of hypotheses for every possible like hyperplane that separates my data, then the VC dimension will be D plus 1. But here we can replace H, and our result for H being deep neural network with rectified linear units, for example, or you can consider polynomial classifiers, or there is a whole. So for regression and completion task, I will not get into the detail, but because this is really about labeling, it's a classification thing. Actually, there is this notion of pseudo-dimension, which naturally extends the notion of VC dimension to the case of regression. So basically, what it does is converting your regression problem into a classification one. You know, but let's not get into the details. It's not that much important. It was more to mention it that we can do that. And the result that I will mention will hold for the VC dimension in the classification case, but also on the pseudo dimension in the regression or completion case. So now, tensor networks. So the idea of tensor network in machine learning, one idea, is like the same way with physics. In quantum physics, people use tensor networks to efficiently represent very high dimensional objects, like the wave function of a system with n particles, basically a vector of 2 to the n, so it's 2 to the n. So we use tensor networks to parameterize these wave functions in such a way that we can manipulate them efficiently. So here in machine learning, it's the same idea. For example, I will talk about just one paper that was published in 2016 by Miles Stoudenmire and David Schwab. So Miles Stoudenmire is a physicist that works on tensor network methods for quantum physics, but also dabbles a little bit in machine learning. And here what they were proposing is basically f of x will be a linear model. But here I will assume that x is potentially some very high dimensional objects, right? So like a big tensor. And so I cannot use like my weight, the weight vector should be on the same side as x, but it's too big. So I will parameterize it as a tensor train decomposition. So look at the sign of the inner product between some weight tensor, but that is parameterized as the tensor train decomposition, and my input. And the idea of the work that we did with Benush is to study the VC dimension of this kind of models.
So once again, what's the sign of this?
Or the sign is just like, if this is a scalar, right? This is an inner product between the tensor. And so it's something like a separator hyperplane. Here, I didn't put a bias term. I mean, it's a real hyperplane. It's not an affine separator. I don't have the plus V, but it's kind of the same idea. And so this is a linear model, right? So we know that, and let's say the dimension is d. So this is an object of d to the 4. We already know that the VC dimension is bounded by d4 plus 1. This is what, because it's a linear model in a space of dimension d to d4. We can apply the little example that we had here, right? But of course, we don't have that many degrees of freedom. So it doesn't make sense that it doesn't make sense. Intuitively, the VC dimension should be way smaller than d to d4. Let's say R is equal to 2. I roughly get 4 times 2 times d parameter instead of d to the 4. So the VC dimension should reflect that. Right? And so it's actually some question that was asked in a paper in 2019 by Cirac, Garre-Rubio and Pérez-García, who will be talking tomorrow about canonical forms for tensor networks. But they were asking basically this question, right? If we look at the model that was introduced in this paper or with other form of tensor networks, can we relate the VC dimension of these models to the bound dimension, to these ranks here, to the size, the number of parameters of my model. And yeah, this is basically what we did in this paper. So the first thing that I want to do in order to define a little bit the problem is to introduce a couple of notation and this idea, yeah, how do I define the set of hypothesis class that correspond to some tensor network structure? Because we want to do that not only for tensor train, but what we were looking for is a very generic result. Given one graph structure, can I relate the bound dimension, the VC dimension to some parameters of the graphs or of the parameters or the size of the objects and things like this.
So did they ask this question for exactly that model with a sign or? Yeah, thinking about this model with the sign, but it naturally extends to regression. Like the X like this. So
the X is actually not like this in the sense that if X is actually a very high dimensional tensor, I cannot manipulate X. And in the application that we have in mind, X is a rank 1 tensor. Yes, that is built from the data, like a quantum.
Yeah, that is why I was.
Yeah, but that's a good point, right? Because I say, okay, we're sparing parameters here, but like this.
Dimension d to the 4, right?
Yeah. But in the actual application of this paper, there is like the paper of Stoudenmire and Schwab that I mentioned, is you have a persisting step of your data, where from your data you build a very high order rank 1 tensor. And this is what you use as your X here. So then you can do all these operations efficiently. No, it depends on your data. And here we don't, in the study that we are doing, we don't assume anything about X. Right? So we're really looking at, and I will define the set of hypotheses that we consider, but we don't make any assumption about X, just about the parameterization of the weight tensor. So just the basic idea to formalize this is that a tensor network is the combination of two things, of a graph structure and a set of parameters. Right? So I have this tensor network here, that's some graph structure, is this object here, where I have the edge, I have the vertices, and I have the dimension of the vertices that are embedded in the graph structure. So here my graph structure is a set of vertices, a set of edges, and a dimension function that to each edge associates an integer, which would be the dimension of this leg. And I have tensor parameters, what I will actually plug into this kind of template, this graph. And so now we just to introduce a little bit more formally the set of hypothesis class that we consider, but with this notation, right, we really consider a tensor network. To get the tensor from the tensor network, we combine the graph structure and we plug in some parameters. So here I have one tensor S of size R times D3, D4 to plug in here, and a tensor T of size D1, D2R to plug in here. And when I combine the two, here I get a tensor of size D1 times D2 times D3 times D4. So now that we have that for any graph structure, we can talk about the set of all tensors that I can realize by plugging any parameter that I want in this graph structure. And interestingly, like this gives rise to a notion of rank, like Lek and Ming did a very nice analysis of this notion of rank that you can introduce on tensors, because for any graph structure, you can talk about what is the minimal size of the inner dimension, basically, and this defines a different notion of rank. So for different properties of my graph, what property do I have for the ranks? Like is it, or the set of low rank tensor closed or things like that? But anyway, I'm digressing a little bit, but very interesting things. And here, this allows us to, if I have a graph structure, I can define this set of tensors. This is the set of all tensors that I can construct by just plugging some parameter, this T2DV, for each vertex in my tensor network. I have some tensor whose dimension is the one that I need to plug in, and I get a tensor in here. So maybe let's look at a couple of examples. Low rank matrices of size m by n. So matrices that are of rank at most R, it's equal to this thing. All the set of tensor networks that I can get with the graph structure like this. I do the product of two matrices, one m by R and one R by n. So this defines the set of all, this is exactly that, all the m by n matrices of rank at most R. For tensor trains, we can define the set of low rank tensor train tensors, like that in the same way, right? We want to say, okay, it's the set of all possible, in this case, fourth-order tensor that can be expressed in this way, right? And actually, this corresponds to the notion of TT rank is a well-established notion and corresponds exactly to that. What is the smallest R that I can find, so that for a given tensor T, I can find an exact decomposition like this. And so now we are ready to kind of frame the problem. What we want to do for a fixed but arbitrary graph structure G, I want to be able to talk about the VC dimension of these hypothesis classes. So for example, for classification, I fix my graph structure G, and I consider all of the set of linear models, right? So it's the sign of this inner product, where W is a tensor that can be expressed with this tensor network structure, with a fixed G. And so this is for classification. For regression, we can do the same thing. We just take a linear model. So this is when I will present results that hold for regression. This is for this class of hypotheses, like linear models, just the inner product between W and X. And for completion, we consider the completion of tensors that have this low rank structure. Right? But let's focus on classification. Okay, so this is the set of hypotheses that we consider. So for example, if we go back to the model introduced by Stoudenmire and Schwab, this set of hypotheses correspond to this, right? So I consider every possible functions so that W can be expressed in this structure. So this is really like this T of Tensor Train. Okay, so now we can go to our results. The first result is about bonding the VC dimension of this class of functions. And so we have the following results, which does naturally relate the number of parameters of the tensor network with the VC dimension. So the VC dimension of this class for an arbitrary G is bounded by 2 times NG. NG is the number of parameters. So I take the size of all of the tensors that are involved in my tensor network decomposition, and this is just the sum of the size of this tensor. And times log 12 times the number of vertices in the tensor network. That is there in the log. So quite natural relation upper bound between the VC dimension and the number of free parameters basically in my hypothesis class. And from that, there we can get this kind of generalization bound, but this is just plugging the VC dimension that we found in the expression that I showed you before. That is a generalization bond as a function of the VC dimension. But here we saw that for any delta with quality at least 1 minus delta, then the gap is bounded by this term that goes to 0 at the rate of 1 over square root of n, but that also has the square root of the number of parameters that appear as something that tells me, okay, the more complex your model is, the more data you will need to get the same kind of accuracy or gap between the two. So the proof of this is not, it has been used before. It has been used notably for matrix completion in 2005, for Tucker completion in 2013, for regression, we did something with my PhD advisor in 2016. And here is a similar technique, but for arbitrary tensor network. And the idea is kind of the proof technique is not very difficult. So it uses Warren's theorem, a very interesting theorem about the number of sign patterns that some system of real polynomials can take. So if you have n real polynomials, each of degree at most v over capital N variables, then the number of sign configuration, right, meaning I look at all the possible variables and look at the sign of each of these polynomials in the system of equation, then is bounded by that. E is the Euler's number, so 4 times EVN over capital N, the number of parameters, to the power capital N. So what does this have to do with what we're doing? Well, the VC dimension is the largest N for which I will find a set of points, x1 up until xn, so that I can shatter it. What does it mean that I can shatter? It means if I look at this, and this thing is a vector of signs, right? Each of these things is a sign. This is the sign of the inner product between x1 and one of these hypotheses. So this is one of these low-rank tensor. I do that for all my input points. But what is this hx? Hx is the sign of, in our case before, this little tensor network. So one particular case of this tensor network with x. So what is this thing? It's a polynomial in how many variables? Well, it's a polynomial in t and s. Here I see it in a polynomial in those two s and t parameters. So it's a polynomial in ng, so which is the number of variables here, which is the size of t plus the size of s of degree. Because when I do this kind of thing, I'm only doing multiplication with component of this, with component of that. So I have an order 2 polynomial. If I had 3 vertices in my graph structure, I would have an order 3 polynomial. Right? So this is where the number of vertices come from. And so then we just apply this theorem to this setting, where the number of variables is the number of free parameters. The degree is the number of nodes in my graph. And the number of real polynomials in this case is the number of points, right? So for every n, I can get a bound on this. So at some point, I will show that this thing is smaller than 2 to the n, meaning I get an upper bound on the VC dimension. So this is nice. It's a very generic result. We can apply it specifically to a couple of examples. For example, for matrices, we get that the VC dimension for the class of low-rank matrices of rank R, is bounded by 10 times R times D1 plus D2. So this thing here is exactly the number of parameters in the matrix of rank at most R of size D1 by D2. So this actually improves a little bit on the previous bound that were known for classification, for completion, where they had an extra log term that was clear. But it's not like a breakthrough in a proof technique. It's just more careful bin counting in the arguments. I think it's just because they didn't care. The log term, you don't really care about it, right? Just leave it there. But we don't have the log term. And for Tensor Train, here we get a bound again that is about dpr squared is the number of parameters, or 3 parameters. So p is the order of the tensor, d is the dimension, and r here is the rank that appears in all the inner dimensions. This bound applies to the tensor train model that I introduced, that was published by Stoudenmire et al. And so this answers the open problem that was listed by Cirac et al. In 2019. So we get an upper bound, but how good is it? Next step was to try to derive lower bound, but this is actually where the technical stuff happens a little bit more, because as I was saying, the proof technique was known, and it was a few difficulties, but nothing really too much. But the more interesting stuff in terms of the proof were to derive the lower bounds. So now we derived a couple of lower bounds for specific graph structure, and these lower bounds show that our upper bound is tight. Right? So for example, for rank 1 tensors, I consider the model of linear classifier with rank 1 tensors, then my lower bound is tight up to the logarithmic factor, right? So my lower bound is the VC dimension is lower bounded by d minus 1 times p. My upper bound is 2dp log of 12p. So ignoring the log term, I'm tight. Basically, we've shown that this upper bound is tight. We cannot do better, because in this part, at least with respect to the log term. Right? So this is the rank 1 here. For CP and Tucker, we derive lower bounds as well, but that are not tight. Here we are missing a factor p. Our lower bound is RD, but we have PRD parameters. For Tucker, we get R to the p, which is the main kind of bottleneck in the number of parameters of the Tucker parametrization, which is this core tensor here. It's the largest thing in the decomposition, but we're still missing this PRD term that corresponds to all those other factor matrices. And for Tensor Train, we get 2 bounds. We get one that is general, that applies kind of always. You can ignore the assumption to the right. It's mostly always the case, which is R squared D. So here we're missing the factor P, but we have an alternative proof where for the special case where we have a third order tensor whose order is a multiple of 3, and where the rank is equal to the dimension, which is a very specific example, but in this case, we can get a lower bound that is of the order PR squared T. So again, tight up to this logarithmic factor. And yeah, so this is our lower bounds that goes with the upper bound, showing that that this is tight. So for example, for D by D matrices of rank at most R, we get that the VC dimension is lower bounded by RD and upper bounded by 20 RD. Right? So we just have a constant factor. Same for a tensor train of rank at most R, whose order is, no, in this case, it's generic. And I think I will conclude rapidly there. I wanted maybe to show some proof, but we won't have the time, and it's already late and it's been a long day. But the proof for the lower bound, I just want to mention this lemma. That is really not difficult to show, but that was very useful. This is what we use to prove all of these lower bounds. It's a simple thing that tells you that if we have an hypothesis, if you have a subset of RD, so you have a set of vectors, d-dimensional vectors, and then we can consider all of those hypothesis class, so the one for classification or regression or whatever, if there exists k indices. So we choose k indices such that they are shattered by V. So what I mean by shattered by V is that it's like k components in my vector, where I can show I can realize every sign pattern only on those k components of these vectors. Then this implies that the VC dimension or the P dimension, the pseudo dimension of this hypothesis class are all lower bounded by k. So I would use kind of the term of finding a lower bound to simply consider the set of tensors And now, when we have a family of tensors, Lorentz tensor, the name of the game is to find a subtensor, so sub-entries, not necessarily contiguous, but such that on this subset of entries, I can realize every possible sign patterns. I can do that for k entries. I directly get a lower bound on the VC dimension. And so all of our construction kind of relies on this thing, identifying special cases in the family, where by setting up some of the parameters and not the other, we are able to achieve this shattering. And so to conclude, so we have the general upper bound for the VC dimension, lower bound for some common tensor network, showing that the upper bound is tight. In the future work, so there is to try to improve the upper bound. Can we remove this log term? It's not that important. No, I mean, it's an interesting question, but I'm not sure we can do. We would need to use a different technique and improve the lower bound for specific tensor network, in particular for a tensor train. I'm quite convinced that we can get a lower bound of the order P r squared D in the generic case, not with this restriction, but we didn't pursue this that much yet in terms of finding a better construction. And something that is interesting, so these tensor networks are somehow connected to neural networks, in some ways, that notably the work of Nadav Cohen and co-authors have worked a lot on this, that there is a connection between tensor networks and some specific kind of neural network that are not used in practice. They're more theoretical model, but that looks a little bit like arithmetic circuits, where instead of your non-linear activation function being this classical activation function like the signal .w that we use in neural network, we use multiplicative interaction as a source of non-linearity. And so basically now we're looking at polynomials, and polynomials that are efficiently parameterized, you get to tensor networks. So there's a nice connection to be done here. We're using some results about tensor networks or about tensor rank. We can say something about this variance of neural network. For example, there's some very nice results showing depth efficiency, showing that for this particular kind of neural network, if you draw a random deep neural network with m neurons, then there is no shallow with probability 1. There is no small shallow neural network that has less than an exponential numbers if the number of parameters of the initial one. So basically, if you want to express the same function, but with the shallow network, we need an exponential size with respect to the deep one, using this kind of techniques. That's all that I have for you. Thank you for your attention.
The last sentence is through VC dimensions.
Actually, what they do is a funny thing. But the real result is about the fact that if you draw a hierarchical Tucker tensor randomly, its CP rank will be exponential in the rank of the hierarchical Tucker. Like if you draw a 3-tensor network randomly, then with probability 1, the CP rank of this tensor will be exponential in R. And then the analogy, is that those hierarchical Tucker correspond to the convolutional equivalent of neural network, with number of layers being the depth of your tree, and the CP1 is kind of a shallow one. So you can use this result, which is only about rank of tensors, different notion of ranks and how they compare to one another, but they convert this result into some depth efficiency, parameter efficiency with respect to depth in neural network. And this doesn't imply the VC dimension, and this is one thing that the result that we get, somehow they don't necessarily agree with what they are saying, but it's just because they're looking at something different, right? The VC dimension is not really like saying, can I exactly represent a function from one class with another class? It's more about the combinatorial nature of doing classification with it. So there are still some interesting things, I think, to explore there.
We have an equation how in low bounds let's say for the Tensor Train.
Yeah.
How the lower bounds behave if you put in additional connections. I mean, the upper bound is still general, right?
Yeah.
So this will change, but the lower bounds, let's say I put like an additional connection.
Yeah. It should be okay, at least with the construction that we have here, which is kind of a silly construction, but it's an interesting. But so that should be okay. But finding a generic, like in the proof that we did, we don't have a generic way. It's really like handcrafted for each specific rank family. So we don't. Maybe there is a way to do something better. That would be nice, right? To have something that depends on the. Like I quickly mentioned that I love this result from Lake and Guillaume that was known also in quantum physics before, but this idea that when you have this rank notion that you define. So for each graph, I can define the notion of rank, and the set of low rank tensors using this notion of rank would be closed in the topological sense if and only there is no loop in this graph. In this kind of very beautiful result. So if we had something like that, that would be like in terms of the generality of it, like looking at are there loops or some diameter of the graph, or I don't know, something like this. That would be really interesting. But no, right now it's more like ad hoc proof for each.
Do our remote participants have some questions? David, maybe?
No, not really. Very nice talk. Happy to hear that this question is solved.
There are how many remaining now? Like 20 or something like that? It was 19.
Yes, exactly. Exactly. Still many things to do. Yes.
Okay. Are there any other questions?
I have a very basic one. You said at the beginning you mentioned different decompositions. For example, the train decomposition. Is it a really decomposition in the sense that every tensor can be decomposed like that?
Yes.
It's just that I need too much high.
No, so you have for all the decomposition, mainly you can find one. There always exists one.
For most tensors, it will be with very high.
Exactly, with very high rank. And for some, there is a problem that I don't know how to solve, but I would like to, because for most of these algorithm, this tensor, this decomposition, if you know that there exists an exact decomposition, you can find it in polynomial time. So I know for Tensor Train, there's an algorithm that I give you a tensor, I know that there's a decomposition of this with this bond dimension, and there's a polynomial time algorithm to find it. For the tensor rank, so we know that it's NP hard, but actually in Genius algorithm, in the case where all of our factor matrices are full rank, give us a polynomial time algorithm to do that. Only in some specific case, right? Of course, not in general. For tensor ring, I'm not aware of such an algorithm. Like, if I know the decomposition, what are the conditions, right? And maybe I'm happy to impose any bound on the rank or thing, but is there a polynomial time algorithm to find a tensor ring decomposition of a given tensor that I know is of low tensor as this tensor ring structure?
Okay. Then let's thank
you everyone for your attention.
And I hope you join us for dinner tonight.
Unfortunately, I have some family obligation.
Family obligations, but we're very flexible, so you can bring your family.
That's true. Unfortunately, I cannot.
Okay, but thanks a lot.
Yeah, I'm very happy to have given this talk.